The final item that we want to consider in this unit is linearization. So up to this point, our analysis has assumed that our systems are linear, and so what that means is that superposition and homogeneity apply. Superposition. And so if you think back to the very first video in this section, we talked about these systems being described by linear time invariant differential equations, and we said that that's going to be the case in most times, but if not, if we have nonlinear systems, oftentimes we can approximate them with linear approximations. So often can be approximated by linear systems. And so the process of doing this is called linearizing or linearization. So we can linearize a system and approximate it with some linear approximation. Once we've done that, we can then use the techniques that we've talked about previously in order to find a transfer function or mathematically model. One example of this that we're not going to go into a lot of detail would be amplifiers. So electronic amplifiers, we essentially say we're not going to be deviating much from a point, so even though we have a nonlinear curve, if we look at a small enough area, we can treat the system as linear. So to sort of graphically look at that to get a better idea, let's consider some function f, which is a function of x, and let's say it's nonlinear, so we have some curve that looks like this. But maybe we're only interested in some small area here, so what we can do is we can linearize that, and we can represent it by some line that looks like this. And so that's if we're interested in this point here. So let's call this point A. Okay. And so we can say at this point A, this is sort of our original spot. So at our point A, we can say we have some value of x and some value of our function. So let's call this x naught, and let's call this f at a value of x naught. So now let's say that we want to know some other value of x. And so to make it easier to see, I'm going to put it out here. So let's say we want to know this. If we're using our linear approximation, of course, we're here. And so let's say this is at some general point x, and that's going to correspond to some f evaluated at that x. So let me come back here for a second and label this blue curve, which would be our linear approximation. Okay, so now, of course, if we look at this, we can say that obviously this is a pretty big difference here. But again, keep in mind that's just so that we can see it. We're saying that as that difference gets smaller, as this difference between x and x naught gets really small, that's going to be a pretty good approximation for our system. So, of course, we could write the slope of this blue line. Let's say we call it m sub a, our slope of our approximation at a, is equal to rise over run, of course, rise over run, and that's approximately going to be equal to f of x minus f of x naught divided by x minus x naught. And so what we can say then, as I was sort of showing graphically, is we keep that same numerator there, f of x minus f of x naught, and then we call this just delta x, and we say let's let delta x go to 0, or approach 0, so it's getting really small. So what we can say then is we could approximate f of x, so we could solve for this term here, which again is what we were looking for. We can say, well, this is about the f at that original point, x naught, plus ma times that really small delta x value. And again, remember this ma is our slope at a. Okay, so that's sort of an informal discussion graphically, so we can kind of get a general idea for what we're trying to do. But if we want to formalize this mathematically, we can use something called the Taylor series. So we can formalize with a Taylor series expansion. However, we're only going to be considering small changes. So clean that up. So because we're only considering small changes from that initial point, So as we're going from x naught to x in this graph here, we're considering that to be really small. That means that we can neglect our higher order terms in our Taylor series. So we're only going to look at our first couple terms. And so what that ends up being is we can say our f of x, so our approximated value, is equal to, and so approximately equal to, again it's an approximation, is f, give me a lot of trouble today, so f at that initial point, x naught, plus the derivative of f with respect to x, so the slope at our initial point, at x equals x naught, times the difference, x minus x naught. And so ultimately what we see is this is the same thing that we came at sort of with our loose definition graphically, but here it's just stated a little more formally with our Taylor series. So what we're going to do in the next video is look at how we can take a nonlinear mathematical equation and linearize it around a certain point.